Every year, billions of square feet of concrete are born in the world, but only a few know about the material that has turned construction on its head. Imagine this. In a single shift, one machine can create almost half a mile of slabs, and the annual output in North America is over 200 million square feet. That's the area of 30 pentagons. How do these lightweight slabs, weighing thousands of tons less, support entire buildings? The secret is hidden in their steel muscles and the mysterious voids inside. Watch till the end, and you'll discover something most people don't even have a clue about. The Slipformer machine crawls along a 600-foot casting bed at a speed of about 4 feet per minute. Doesn't sound too quick? Well, let's do the maths. That's 200 feet an hour. That's almost the length of an Olympic swimming pool, born from concrete in less than an hour. In a single 10-hour shift, one of these beds can churn out nearly half a mile of perfectly formed concrete slab. And a big plant might have several of these beds. This isn't just building, it's a conveyor belt running at a speed unthinkable for traditional, pour-on-site concrete. And now for the main trick, the hollow cores. These holes inside aren't just for looks. They slash the slab's weight by almost 50% compared to a solid slab of the same thickness and strength. What's the payoff? Picture this. You're building a 100,000 square foot office block. If the floors were made from standard, solid concrete, they'd weigh about 5,000 tons. But with hollow core slabs, just 3,000 tons. We've just stripped 2,000 tons of dead weight from the building. That's the weight of about 500 adult elephants that the foundations, columns, and beams no longer have to carry. This allows the entire structure to be lighter, more slender, and most importantly, a whole lot cheaper. But how can such a light slab be so strong? The secret is in those tensioned steel muscles. The concrete used in these slabs isn't what you'd find on the footpath. It's high-strength concrete that can handle pressures over 8,000 pounds per square inch, while standard concrete manages only 3,000 or 4,000. And the steel strands inside are tensioned with such force that they create a constant state of compression within the slab. Because of this, a hollow core slab can easily span 60 feet with no intermediate support at all. 60 feet. That's the width of a professional basketball court. Imagine a huge open space with not a single column in sight. That's exactly why these slabs are a favorite for building car parks, supermarkets, and open-plan offices. Every year, over 200 million square feet of hollow core slabs are produced in North America. The number is just staggering. It's enough area to build 30 colossal buildings like the Pentagon. Every single year. This isn't just a building material. It's an entire industry built on speed, efficiency, and clever use of resources. So these figures aren't just dry data. They're proof that sometimes, to get stronger, you just have to get rid of the unnecessary stuff on the inside. It all starts not in a concrete mixer, but on a massive, perfectly flat runway inside the workshop. This is the casting bed. Imagine a perfectly smooth, polished steel track a few feet wide, but 600 feet long. That's longer than 2 footy fields, end to end. Beneath this track run, pipes circulating hot water or steam to keep it warm. This is the perfect cradle for the birth of our future giant. At both ends of this track stand massive steel abutments, anchored into a thick concrete foundation. They're like steel teeth sunk into the earth, and their job is to withstand simply inhuman loads. Between these two abutments, high-strength steel strands are stretched. This isn't your average wire. It's several steel filaments twisted together, each capable of holding the weight of a car. They are laid out along the entire 600-foot length of the bed, forming the slab's future skeleton. One end of each strand is securely fixed in an abutment. The other is hooked up to a giant hydraulic jack, and this jack starts to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. That's like hanging 3 full-sized utes off each thin strand. The steel muscles tense up, becoming as taut as the strings of a giant guitar, storing a colossal amount of energy. This is secret number 1, pre-stressing. When the steel skeleton is strained and singing with tension, the star of the show appears, the Slipformer. This is one of the most incredible machines in the construction world. Imagine a strange, low-slung, self-propelled creature, slowly crawling on rails along our long bed. It has a large hopper on top, which is filled with concrete. But this isn't your typical liquid concrete. It's what's known as zero-slump concrete. It's so dry it looks like damp earth. If you picked it up, it wouldn't flow through your fingers. And so, this machine begins its slow journey. Inside, a real marvel takes place. Firstly, the concrete from the hopper is fed downwards, enveloping our tensioned steel strands. Secondly, special vibrators and compactors ram this dry mix with incredible force, making it unbelievably dense. And thirdly, and most importantly, inside the machine are special forming tubes, or mandrels, which vibrate as they push through the concrete, leaving behind perfectly round, smooth voids. The machine, like a giant concrete snail, slowly crawls forward, leaving in its wake a perfectly formed, endless concrete slab with hollow cores inside and tensioned steel muscles hidden within its body. Because the concrete is so dry, it holds its shape instantly and doesn't sag. This is secret number 2. The voids, which make the slab 50% lighter than a solid one while barely reducing its strength, as the top and bottom sections do most of the work. Once the machine crawls to the end of the 600-foot bed, its job is done. But our slab is still green and weak. It's time for a spa treatment. Workers cover the entire length of this concrete ribbon with huge insulating tarps, like blankets. Hot steam is then pumped under these blankets. This creates a sauna effect, which dramatically speeds up the chemical reaction of the concrete curing. Under normal conditions, concrete needs weeks to reach its full strength. But in this hot, humid atmosphere, it achieves the required strength of over 5,000 pounds per square inch in just 12 to 24 hours. When the concrete has set and become hard as rock, it's time for the release. Workers slowly let off the pressure on the hydraulic jacks. The tensioned steel strands, now permanently bonded to the concrete, try to shrink back to their original length. But the concrete won't let them. As a result, this massive compressive force is transferred to the concrete slab itself. Now it's not just a concrete slab, it's pre-stressed or compressed. This means that when a load from above tries to bend it, it first has to overcome this built-in compressive force. This is what allows it to span huge distances without extra support. And the final act of this performance, the cutting. A giant saw travels on rails along our long concrete ribbon. It's a monster with a massive blade coated in industrial diamonds. With a deafening roar and a spray of sparks and cooling water, this saw cuts the slab with incredible precision into sections of the required length, according to the order. The finished, perfectly flat, lightweight, and incredibly strong slabs are then picked up by giant cranes and loaded onto trucks. And just like that, after a journey from a tensioned steel string to the slow crawl of a concrete snail and a final diamond cut, this brilliant piece of engineering is born, ready to become the fast, efficient, and reliable flooring in the buildings where we live, work, and play. Every year, over 4 billion miles of fiber optic cables are produced worldwide. That's enough to wrap around the Earth more than 160 times. But few people know that their journey begins with sand. A special kind, whose purity is measured in parts per million. Because even one microcrack can destroy a signal that's racing for thousands of miles at the speed of light. What is this magic? How does ordinary sand turn into transparent threads, thinner than a hair, but stronger than steel? Watch closely. At the end of this video, you'll learn a secret you've never heard before. To create a thread capable of transmitting light at a speed of over 186,000 miles per second, you have to start with sand. But not just any sand, only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, sand with a silica content of over 99.9% is used, which means in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, and air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop, and all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large, transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod, and this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break. Cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube, or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin, or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire, so the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this without a single break, without a single scratch. Because even a micro crack and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe, resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation.